Hello students, now in this video let us see solution of congruences. Solution of congruences. Already we have seen the definition of linear congruences. So here let's see what is the how to obtain the solution of it. Now first of all let f of x is equal to an x raised to n plus an minus 1 x raised to n minus 1 plus so on up to a1x plus a0 be a polynomial with integral coefficients an equation f of x congruence to 0 modulo m where this m is strictly positive is called congruence equation modulo m, and if there exists any x which satisfies this congruence equation, that is known as the solution of that congruence equation. So for that, if there exists an integer x naught such that f of x naught congruence to 0 modulo m, then x naught is called a solution of f of x congruence to 0 modulo m. For example, x square plus 2x plus 2 congruence to 0 modulo 5, then here this is a polynomial. Here we have to put x such that value of x congruence to 0 modulo 5 means remainder should be 0 in that case. So here x is equal to 1. If we put x is equal to 1, so it will be 1 square plus 2 into 1 plus 2, so it will become 5. 5 congruence to what? 0 modulo 5. So it satisfies for x equal to 1. So x equal to 1 will become a solution for this congruence equation. Also x equal to 2 is also solution of it. Are the solutions. You can check on your own for x equal to 2. Again, x square minus x plus 4 congruence to 0 modulo 5 has solution x equal to 3. Also, x square minus x plus 4 congruence to 0 modulo 10 has solution x equal to 3 and 8. Again, now some of the congruence equation doesn't possess a solution also. So here x square minus x plus 4 congruence to 0 modulo 7 has no solutions. Okay, now note that the solution of are the solutions of congruence equation f of x congruence to 0 modulo m. Obviously it depends on this m, depends on value of m, value of m. If x naught is one solution, is one solution of x naught is one solution of f of x congruence to 0 modulo m, then all integers y such that y congruence to x naught modulo m. All integers y. These all integers y are what? Are the solutions of this congruence equation f of x congruence to 0 modulo m. Now for this, let's take an example for this node. Example for the node, as 3 is a solution of x square minus x plus 4 congruence to 0 modulo 5. So 8, 13, 18 and so on are also solutions of x square minus x plus 4 congruence to 0 modulo 5. Okay. Let's see next definition. Let x1, x2 and so on up to xn be a complete residue system. Modulo m, then the number of solutions of f of x congruence to 0 modulo m is the number of xi such that f of xi congruence to 0 modulo m. Again, the next definition is of degree. Let f of x equal to an x raised to n plus an minus 1 x raised to n minus 1 plus so on up to a1x plus a0 be a polynomial with integral coefficients if an is non-zero or an doesn't congruence to 0 modulo m, then degree of f of x or the degree of f of x congruence to 0 modulo m, this congruence equation has a degree n, is equal to n. The degree of that congruence equation is n. If an congruence to 0 modulo m, then if there exists largest integer j such that aj doesn't congruence to 0 modulo m, then degree of the congruence equation f of x congruence to 0 modulo m is equal to g. Whatever the coefficient for which the remainder should not be 0 for modulo m, then that will be what? The degree of that congruence equation f of x congruence to 0 modulo m. Right? For example, 6x square plus 3x plus 1 congruence to 0 modulo 5. So here f of x is 6x square plus 3x plus 1. Okay. Now is of degree 2, as the coefficient of x square, that is 6 doesn't congruence to 0 modulo 5, while 6 congruence to 1 modulo 5. That's why the degree of this congruence equation is what? 2. Again, second example, 6x square plus 3x plus 1, suppose the same polynomial I am taking, congruence to 0, let me change m, congruence to 0 modulo 2 suppose. Now is of degree, now look at here, 6 congruence to 0 modulo 2. So here 6 congruence to 0 modulo 2. But here the coefficient of x, that is what? 3. This 3 doesn't congruence to 0 modulo 2. That's why here the degree will become what? 1. The degree is 1, as 3 doesn't congruence to 0 modulo 2. Same polynomial, but if we change m, the degree will change. Again, one more. Suppose again the same polynomial, simply we change the m, 0 modulo suppose 3. Now here 6 congruence to 0 modulo 3, 3 also congruence to 0 modulo 3. So here the degree is what? 0. Only a constant term will remain here, is of degree 0, as 6 congruence to 0 modulo 3 and 3 congruence to 0 modulo 3. Both of them. Fine. Now from there let us write one note for the degree of a congruence equation. Note says that the number of solution of f of x congruence to 0 modulo m does not depends on degree of f of x congruence to 0 modulo m. Solution doesn't depend on the degree. Also the degree of f of x congruence to 0 modulo m does not depends on does not depends on degree of f of x. It depends on m. It depends on the value of m. For example, 6x square plus 3x plus 1 has degree 2. Polynomial has degree 2, but the congruence equation congruence equation 6x square plus 3x plus 1 congruence to 0 modulo 3 has degree 0. Second example, x square minus 7x plus 2 congruence to 0 modulo 10. This congruence equation has solutions x equal to 3, 4, 8 more than degree of the congruence. Now the degree of this congruence equation is what? 2, as 1 is a coefficient of x square here and 1 doesn't congruence to 0 modulo 10. So the degree will be 2, but the solutions are 3 in number. So they are more in number. So the number of solutions doesn't depend on a degree, and the degree doesn't depend on f of x, while it depends on what? The value of m modulo what does that. Fine. Now let's see one theorem. Now here this only the statement of this theorem. If d divides m and d is greater than 0, strictly positive, and if x naught is a solution of a congruence equation, f of x congruence to 0 modulo m, then x naught is also a solution of f of x congruence to 0 modulo d. Means if x naught is a solution of a congruence equation f of x congruence to 0 modulo m, then in place of m, if we put any divisor of it, which is a positive divisor of 8, still x naught will become a solution of that congruence equation f of x congruence to 0 modulo d. Fine. Now we have to see one theorem with its proof about the number of solutions of a linear congruence. So let's see that. Theorem. Let a, b are some integers and m is a positive number. D is a GCD of a and m. Then a linear congruence ax congruence to b modulo m has d number of solutions. If and only if d divides b. If x naught is one solution of Ax congruence to B modulo M, then other solutions are x equal to x naught plus m upon d times k, where k is any integer. Now let's prove this proof. Now here if and only if, so both way implication. First of all, this one should be given to us. Suppose Ax congruence to B modulo M have a solution, say x naught, and we will prove D divides B. Fine. So suppose Ax congruence to B modulo M have a solution, say x naught. If x naught is a solution of it, that is Ax naught congruence to B modulo M. Okay. So by definition of congruences, we get here M divides Ax naught minus B. That is, then again applying the definition of divisibility, we get Ax naught minus B equal to M times some integer. K is any integer. Fine. So this is Ax naught plus, now let me take this mk to this side, so plus m into, let us say, minus k is equal to what? B. Call it as equation number 1. Now also it is given to us the GCD of A and M is what? D. GCD of A and M is D. So what does this say? This D divides A and D also divides what? M. D also divides M. So D divides A, so that gives us A is equal to D into K1 and M equal to D into what? K2. For some K1, K2 are what? Integers. K1, K2 are some integers. So from this our equation 1 becomes dk1 x naught plus dk2 into minus k is equal to what? B. So that is same as to say B is equal to D times k1 x naught minus k2 into k. So this is one of the integer, because all these k1, k2, k and x naught all are integers. So this is an integer. So this gives D divides what? B. Fine. Now this is forward part. Now conversely, suppose D divides B, where D is GCD of what? A and M. Fine. Now our claim is here, claim that Ax congruence to B modulo M has a solution. Fine. So as D divides B, so this says B is equal to D into some integer. Also D is the GCD of A and M. So this gives there exists some integers x naught, y naught such that there exists some integer x naught, y naught such that D is equal to A x naught plus M y naught, linear combination M y naught. That is dk is equal to A x naught k plus M y naught k. I have multiplied throughout by k. So this dk is nothing but what? B. So this gives B is equal to Ax naught k. We can say this as 1. So from, or let me say 2. From 2 we can write it here. So my naught k. This is from 2. Fine. Now here we get Ax naught k minus B is equal to m into minus y naught k. So this says m divides Ax naught k minus B. So this gives us Ax naught k congruence to B modulo m. This shows that Ax congruence to B modulo m has a solution x equal to what? X naught k. Now if x naught is one solution of Ax congruence to B modulo m, then what we get? Ax naught congruence to B modulo m. So Ax naught congruence to B modulo m, this gives, that is same as to say B congruence to Ax naught modulo m. That is B congruence to Ax naught modulo m. Now here Ax congruence to B modulo m, B congruence to Ax naught modulo m. So this gives Ax congruence to what? Ax naught modulo m. But we know A and m are having adjacency D. So here we get, from this we get this x congruence to x naught modulo what? M upon D. As D is the GCD of whom? A and m. Fine. Now from this, if we apply the definition of congruence and divisibility, we get the required part. So here what does this say? This says m by d divides x minus x naught. That is same as to say x minus x naught is equal to m by d times some k, where k is what? An integer. So this gives x is equal to x naught plus m by d times some k. K is an integer. So x naught is one solution, then this gives us other solution of this congruence equation, linear congruence. Fine. Now this is about this theorem. Now let's write one remark from this theorem. Remark: if D doesn't divide B, then Ax congruence to B modulo m has no solution, and second, if A and m are relatively prime, then Ax congruence to B modulo m has unique solution. Okay. Now here we will stop. In next video we will see some examples on these linear congruences, and also we will see the theorem of Chinese remainder. That theorem is for solving the system of linear congruences. System of linear congruences. How does we can obtain a solution for system of linear congruences, and examples on them. Thank you.